yeah, which describes one of the electronic states in 2 dimensions, yeah, for instance. And upon an absorption of a photon, it goes to, let's say, one of the excited states. And there is one green sheet sitting close to the red one. What happens? So after absorption, this molecule comes down either by fluorescing to the green sheet, and then after coming down, this green sheet anyway is in close proximity with the red one here at one and at this location, and then this wave packet sees this channel here through this point and then comes down to this red sheet, yeah, and then similarly this can go back to its initial configuration. So what's happening? So this is, I mean, here at these points, these are called conical intersections. At these special points, what's happening is that the nuclear wave packet strongly coupled to the 2 electronic states are highly strongly correlated with each other. So they share the information of nuclear amplitudes. So that's what is happening. Yeah? And the dynamics around this point where these energies are close to each other is actually governed by those non-adiabatic coupling elements that we have seen. Yeah. So I mean, this is the nuclear wave packet, the time-dependent Schrodinger equation that we got for this, let's say, this nuclear wave component, and then some of the nuclear wave packet is actually, when it comes around this region, it experiences strong coupling with the nuclear amplitude already present in here, or zero amplitude present in here. Some of the amplitude is transferred. It's like a funnel, yeah. So you pour the kerosene and it drops down. So that's something like that. So in multi-dimensional, these are conical intersections because the topography of the potential energy surface, if you zoom in, what happens? It looks like a conical topography. Yeah. So one can, I mean, using a 2x2 Hamiltonian, one can actually see whether the eigenvalues of such a Hamiltonian resemble the cone equation. It's quite easy to see. Yeah? Anyway, so these special point intersections, and they lead to all kinds of complex molecular dynamics. For instance, there is an ultra fast radiationless decay. I mean, you tend to see the population here without emitting light. Yeah, and then the the molecule made an excursion over all the potential energy surfaces. The spectrum, if you observe, it's going to be very complex because it spanned all the vibrational states of these different surfaces, and all the spectrum will be highly complex, right? And then you see, I mean, you started here. If you think this as one of the reactant, and you ended up with some product here without having to do anything, any thermal activation or anything. Yeah. So these, I mean, it leads to, I mean, there may be multiple wells, some in the multidimensional potential energy surfaces. So they form different reaction channels or products. So at these special points where the electronic states touch each other, conical intersections, the surface topography resembles the cone equation. The electronic and nuclear motions are strongly coupled, and that's that we have seen in the time-dependent Schrodinger equation for the nuclear part. Okay. So just refreshing, we wrote down our time-dependent Hamiltonian and then I made it in 3 parts because I subsumed all other parts into this electronic Hamiltonian, and then these read as follows. You're familiar with anyway. And then we get these terms, and then this one gives us the potential energy surfaces. That's what I mean, these terms may be slightly different from what I wrote down, but essentially it's the same thing. And then this term we showed that at conical intersections where the degeneracy of the 2 potential energy surfaces is, this term, if you're using Hellman-Feldman relation, form it to be proportional to 1 over EI minus EJ, for instance, or M minus N. So at CI, these 2 are equal, so it blows up. Yeah. So therefore, we resort to so-called diabatic representation in order to deal with such. I mean, numerically we have to solve, right, because it becomes singular. So what are the ways of solving numerically such an equation? So one of representation, infamous representation, is diabatic representation, where we choose the basis functions for the electronic basis functions in the unsas, initial unsas reference configuration, and then it's an easy trick that these will go to 0, and this now assumes coordinate dependent couplings here. Yeah. These are the couplings due to kinetic energy term in the Hamiltonian, and since they are becoming singular here, we would like to transform them away, and then the couplings reappear here as coordinate dependent couplings when you make this transformation. And this is easy to deal numerically, because there will not be any singularities. Okay, so one of the famous Hamiltonians that I just want to illustrate how this kind of coupling looks like in the potential energy is the so-called linear vibronic coupling Hamiltonian. For instance, you have a ground state and two excited electronic states, color coded, and they are coupled. For instance, I mean the matrix of the, let's say, 2 by 2 Hamiltonian, the 2 in the basis of electronic states, we are representing this molecular Hamiltonian. Looks like this. So you have two electronic states, and anyway, this is the kinetic energy part untubbed along the vibrational coordinate, and when they couple with each other, so they displace, the minima get displaced to, let's say, this position here, and this one get displaced here, and also they have a splitting which is shown here. So they tend to split. This splitting is given by so-called off-diagonal potential energy couplings. So this is the potential energy matter. You see, and the gradients at this reference configuration or at the equilibrium configuration is given by these intrastate couplings, so-called intrastate couplings. You see, in this whole Hamiltonian, we haven't have any couplings due to kinetic energy part of the Hamiltonian. All the couplings are actually residing in the potential. So such a kind of Hamiltonian is called diabatic Hamiltonian. So this is just simple illustration. So it's easy to work numerically, and there are a number of diabatation techniques how to obtain these coupling parameters and other things. So I'm not getting into that. Okay. So I mean, this was already told, but pictorially I'm just showing. So if you have a wave function evolving on one state, so let's say a general wave function, in the 2 by 2, I mean, you have two electronic states and they are coupled. How the non-adiabatic couplings affect the motion of each the nuclei on each of the surfaces. So the diabatic Hamiltonian, which I mentioned, you have the kinetic energy part and the potential energies and the couplings. So the nuclear component, one of the potential energy surface sitting here, let's say, is coupled to the nuclear component that's sitting somewhere here, and the nuclear motion is coupled. That's trivial. That's what we have seen in the time dependent Schrodinger equation. And then this coupling can be controlled via this non-adiabatic the nuclear dynamics can be controlled with this non-adiabatic coupling, tuning the non-adiabatic coupling here, because this says the mean position of the nuclear wave packet, and it can be tuned with respect to the phase difference between these two electronic states here, and then the non-adiabatic coupling between them. So these are the possible ways to tune this phase, of course, but non-adiabatic coupling is internal, and this is something that we cannot. There are something called you can tune the non-adiabatic couplings as well, so-called laser-induced conical intersections, people call to an extent. So it's a strong field effect, but in the weak field regime, one can play with this phase with the lasers and then tune the mean position, nuclear dynamics. That's a different story. Okay, and then not only the nuclear dynamics that gets affected because of this coupling of nuclear amplitudes on two different surfaces, it's the electronic properties that also get affected. For instance, it is shown that electronic decoherence via this coupled nuclear dynamics occurs on ultra-fast femtosecond time scale. Let's say you see what's going on in this expression here, which is the purity of the electronic states. it's sheerly dependent on this. If you write the density matrix down for this wave function, so it becomes the 2 by 2 uh, uh, matrix, and then the purity can be estimated using, I mean, one can derive this, you can find that in the paper. So what enter in the definition of the purity is only nuclear amplitudes evolving on two surfaces and the non-adiabatic couplings and the phase of the electron. So all these together conspire to actually control even the electronic coherence. Yeah. Okay. So how to solve such a dynamics? You can resort to numerically exact method or MCDH method. So numerically exact method means you just define the basis functions for each nuclear degrees of freedom or the electronic degree of freedom, and then brute forcefully diagonalize it, or the Hamiltonian at each point of time, and then go on. That's one thing. Or use split operator techniques, and there are other techniques. And there is this MCDH method due to Lenz and Dieter Meyer. So it has a great reputation in our community, this method. And then once you solve this time dependence, you get so-called autocorrelation function, because the nuclear wave packet evolves and you overlap with the evolved nuclear wave packet with the initial nuclear wave packet, and then you can construct the autocorrelation function. Fourier transformation of this autocorrelation function gives you directly the spectrum of the system. For instance, you see, so here if you want to obtain the spectrum pertaining to this system, for instance, so you take the nuclear wave packet at each instant of time, which is evolving on these complicated potential energy surfaces, and then overlap with that initial wave function which is sitting here. Yeah, you overlap this instant of time, this blue with this green with this green with this, and then construct so-called autocorrelation function, because it's overlapping with its own wave function initially defined at initial time. And then Fourier transform this, you get the spectrum of the system. That means what all eigenstate that it has actually scanned through during this excursion, you get that. Yeah, that's what is a spectrum. Yeah, or alternatively, if you don't want to perform all these time dependent dynamics and all, you construct the Hamiltonian in any Fourier grid basis or whatever, diagonalize it, and then you get the spectrum. But this is the non-trivial transfer. Diagonalizing a Hamiltonian matrix for a molecule having, let's say, 10 degree of freedom. It's non-trivial, for instance. Yeah. Yeah. So let's apply these techniques to study so-called ring current phenomena in molecules. Let's see how the non-adiabatic couplings affect the so-called electronic dynamics in molecule. Okay, this is the just application of. How much time do I have? 10 minutes. Okay, I managed to finish it. Okay, fine. Okay, ring currents you are all familiar with, right? Because you have let's say from your NMR, if you have studied masters in chemistry, NMR. Nuclear magnetic resonance spectroscopy, anybody studied? Okay, it doesn't matter. Anyway, so ring currents are known to actually affect the chemical shifts of protons in a magnetically active, I mean, in a planar conjugate molecules of this kind. And they were also shown to play a crucial role in explaining the spectral shifts in, let's say, vibrational circular dichroism, or in the UV visible regime. So this is just a familiarity, just to make you familiarize with where you can find ring currents applications, for instance. And the origin of these ring currents actually lies in the degeneracy and the symmetry. The symmetry of the system. Yeah, the symmetry directly implies the degeneracy of the system. If it has sufficient symmetry, let's say at least C3. If a molecular system has at least C3 symmetry, it is guaranteed to possess doubly degenerate electronic states, and these degenerate electronic states happen to be the eigenstates for the angular momentum operator, and hence the electron be present in these states feature some angular momentum. Yeah, because they happen to be the eigenstates of the electron. So one can simply work out what is the ring current associated with, let's say, particle on a ring model. on a ring. So it's easy, it's trivial to calculate. Okay, given that, so in molecules and atoms, you find such doubly degenerate electronic states featuring ring current in one of these directions. When it follows one of these symmetry criteria, at least it should have C3 symmetry axis. And then the way to trigger these ring currents is by applying so-called circularly polarized laser pulse, and it's defined in this fashion. But for now, we don't worry about the light matter interactions and the dynamics driven by it. We just see the consequence of non-adiabatic couplings. Okay. So yeah, these are all past studies how people have neglected these non-adiabatic coupling effects and studied the ring current phenomena. Claimed that okay, you can produce gigantic amount of magnetic fields due to these ring currents and all, but we see what vibronic couplings can do. Yeah, absolutely, yes. That's it. So theoretically, that comes from the doubly degenerate electronic states. They are called ground state ring currents because when you apply a magnetic field, what happens? The ground state perturbatively couples with these doubly degenerate states, which feature some ring currents, which support some ring current, and hence the ground state inherit that ring current aspect. And then as long as you apply magnetic field, you have a steady current revolving around the magnetic field axis. Okay. So the classic model for vibronic coupling is called Jantelar model. So let's say you have a conical intersection between one of the adiabatic sheet and the lower adiabatic sheet, and here is where you expect to see, in this model, strong vibronic coupling phenomena. So I just took, let's say you have two electronic states coupled by nuclear coordinates in the potential energy matrix. This is a diabatic Hamiltonian. Yeah? What happens? You choose a proper basis for diagonalizing this Hamiltonian. Since this is a simple Hamiltonian, I can afford to diagonalize it and get its eigenvalues. Following angular momentum criteria and things like this, I'm not getting into the details of the model here, but let's assume that you could diagonalize, identifying a proper basis which conserves the angular momentum, total vibrational and electronic angular momentum of the system, and you get the so-called eigenstates of this particular Jantelar molecule. You see, these are the eigenstates you are already familiar with, right? We have written the Born BH expansion just now. Nuclear coefficient multiplied by the corresponding electronic state, nuclear coefficient multiplied by the other electronic state. These are the two electronic states, and they have the nuclear coefficient. This is the BH expansion that we have written. So when you diagonalize this, you numerically get the composition of this electronic state and this electronic state via these coefficients in each of the vibronic states. Yeah? These are vibronic because you have vibrational part and an electronic part here. That's why I call vibronic state. Yeah. And it so happens, if you just want to see the current featured, current supported by this vibronic eigenstate, following some little bit lengthy derivation in the paper, you obtain the ring current supported by this particular vibronic state is sheerly dependent on the population of this state minus the population of this state, the population imbalance of these two electronic states, which are sheerly governed by the nuclear coefficients here, the populations of individual electronic states. And these nuclear coefficients are in turn governed by the nature of the vibronic coupling, because that's how these coefficients evolve on these two surfaces, right? Okay, so if let's say if the coefficients are time dependent here, like in general case, so is the current associated with this vibronic eigenstate. Okay, we calculated the currents associated with different eigenstates of this molecular system, and we plotted them for different coupling strengths, different vibronic couplings. It so happens that all the vibronic states, let's say initially the electronic states are not coupled with each other. Yeah, when there is no vibronic coupling, the electronic states possess their respective angular momentum. E plus has plus h cross angular momentum. E minus has minus h cross angular momentum, and then as you start activating the vibronic coupling, these two states couple with each other, and and the net angular momentum gets suppressed, right? That's what is happening for all the eigenstates of the system. But two eigenstates I highlight here just to illustrate the point that this is the optically bright eigenstate of the system, and if you monitor the currents of this, it also possesses more or less the same behavior. And this is this is the blue state is the state associated with the maximum amount of current at a given coupling strength. So which means that it says that the optically bright state doesn't have to be maximally state with maximum current, I would say. Yeah. So one can trigger these currents by applying circularly polarized laser pulses at different portions of the spectrum, and so these all vibronic. So that's what the vibronic coupling effects suppress the net electronic ring currents. That's what is the message. Yeah. And then the other message is that the vibronic coupling effects are also responsible for so-called inverse ring current states, but I stop it here, and then I have to define inverse ring current state and things like this. Okay, so this is MCDDH. I have no time. So if you have more, this is a 2 by 2 state model. We have propane molecule, which is 12D, 15D model. So we used MCDDH to get the spectrum and calculate its ring currents, because one of the experimental groups inspired by our work, they performed this photoelectron circular dichroism spectroscopy and monitored some ring current signals, and then they asked us to simulate that. We need to simulate the spectrum first and target it with light pulses later. That's our task. So yeah, this is MCDH, but I won't go in there. Yeah. Okay, stop it here. Yeah. Yeah. Thank you. Yes. Yes. Magnetic. In reality, I mean, you can produce magnetic fields, but not the extent that they claim. That I did not. We were only interested in the current part. We not. I didn't, because the way they calculate the magnetic field using Biot-Savart's law due to this current, and somehow we are suspicious about how to do that. Yeah, 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 yeah. That's one good input. Yes, yeah. Because we are heavily relying on the phenomena rather than the. So that's only theory, but yeah, yeah. So yeah. So that's how the implications of vibronic couplings on the photoexcited phenomena in particular. This is one. I'm sorry. And this is another spectrum which you, let's say this is the spectrum that you have just seen above as a sticks. Yeah. If you compute with MCDDH, time dependent dynamics, that was with diagonalizations, therefore you could see sharp sticks. But here you could not see that because you cannot resolve them. You can only propagate on finite time and then get this spectrum factorized. And if you couple this molecule, because I mean molecule means it's spectrum in some sense. So if you couple this spectrum to a cavity mode, so the spectrum gets split down, and so you form so-called polaritonic states, and that too you can compute with MCTDH. So, but I refrain from saying anything about MCTDH. I'll do that. Okay. Yeah. Yeah, yeah.
Just to get an idea for me and I guess.
Yeah.
Without MCTDH, it's more crazy.
Yes, yes, yes.
How long does it take to do it with MCTDH?
How much time?
Yes, how long to run the simulation?
Um,
Roughly, I mean, is it minutes, hours, days?
yeah, it's definitely for the spectrum part. It doesn't take much time. If you want to propagate it with respect to any, I mean, in the presence of any laser pulse, then it takes horrible amount of time. Spectrum, it took, I guess, for 50 femtoseconds, it took almost 1 day roughly.
One day.
Because we have very, this is a very flexible molecule. We had to use long grid ranges and lot many denser points and things like this. The potentials are very shallow. I did not show the potential.
Without NPTEL, it's nearly impossible.
Yeah, it's nearly impossible. Yeah, absolutely, yes.
Many
Yeah,
experiments,
yeah,
that's
yeah,
really the power of
yeah,
NPTEL.
yeah, yeah, yeah. Thank you.
So, Len, thanks again.
Thank